Hey friends, we are back for another edition of some early introductory quantum mechanics. Before we get started on that, just a reminder that the traffic light is the PLC. I did post that on Tuesday, yesterday afternoon for me. And that is just starting to get you thinking about, okay, final is near. It's going to be, this is week 13, so we've got 14, 15, so we've got about 3 weeks to the final. So start thinking about reviewing the thermodynamics, start thinking about reviewing ray optics, wave optics, and kind of the things that maybe didn't get stuck the first time around. So let's see what we can do about getting that squared away. That's going to be, again, a Friday thing. Once again, an easy one to let slip through the cracks, so please be sure to submit that. And homework 8 is almost posted as of right now. I haven't yet, but I will later today. So let me do Thursday next week, which is the 13th. And there'll be the usual quiz on that day. We'll have likely one more homework assignment after that, but it will not be to turn in because I will not be able to grade it and get it back. So I'm hopeful that I'll be able to grade that when we get it back. I do have a bit of a backlog right now, but working through it, and we'll get to it at some point. So let's continue talking about the introductory ideas, the ideas that led to a realization that classical physics was not quite 100% doing the job at all scales. Okay, so it does pretty well, as you probably know. We talk about the gravitation of planets. We talk about using Newton's second law, Newton's laws of mechanics for NASA uses them for space flights. And we use them all the way down to really small. We can talk about little particles of dust and things like that. But eventually, once we get down to a really small scale, right, the atomic scale and the behavior of light, things get to be a little bit less intuitive. So I have the examples on Compton effects to do today, and then we'll start getting into some more of the reasoning and some more of the physics that took place after that in order to try to push forward some understanding about the quantum mechanical world. So I left you off last time when I talked about the Compton shift. This is known as either the Compton shift, possibly also known as the Compton effect. And it's a situation very similar to the photoelectric effect in which light comes in and strikes relatively stationary electrons. Now, I talked about this in the previous video, so the similarities of light coming in, striking electron, giving the electron energy, very similar things. In this case, however, the photon does only scatter off the electron, whereas in the photoelectric effect, we essentially consider that the photon has been absorbed, and it's a convenient model to use. Okay, so in this case, the photon does survive. It hits the electron, pushes the electron out, just like a classical scattering problem, and both objects scatter away at different angles. And using conservation of momentum and conservation of energy, we came up with the Compton shift formula, in which we consider a photon coming in this way with a particular wavelength and striking a relatively stationary electron. I'll make the electron larger here, like that. And then as they both kind of go off in a glancing type of collision, okay, so we orient the Compton shift to the scattered photon angle. And remember last time we talked a little bit about the relative size of the wavelength after it's been scattered. Since we think of energy as being related to hc divided by the wavelength, okay? Since the energy of a photon is hc divided by wavelength, this is a photon of energy. So if the energy is decreasing, because in this case the energy of the photon will be decreasing from here to here, okay? The photon, it's not technically the same exact one, but nonetheless, whatever photon energy is over here will be larger than the photon energy over here. The reason is because some of that energy got given to the kinetic energy of the electron, and so we would diagram that out in a bar chart by saying that I have initially some initial photon energy due to the incoming photon, which then gets transferred into something the same size bar here, but this piece here would be the energy of the outgoing photon, hc over lambda prime, and since that energy is lower than this energy, the wavelength has to be higher in order to make that happen. The rest of the energy is in the kinetic energy of the electron. That's Ke electron. Okay, so another conservation of energy problem. This is exactly the same type of bar diagram I drew for you in the photoelectric effect. We did the momentum conservation last time, and we came up with the shift in wavelength, which tells us how much the wavelength increased in the new photon after the scattering. And it was equal to this. Okay, where hc is our normal 1240 eV nanometers constant, and mc squared is the rest energy of whatever is doing the scattering. And in this case, we consider electrons. In general, we consider electrons, but it's, as mentioned last time, it's certainly okay to consider protons. It's okay to consider things that it's okay to consider things that photons would bounce off. Whatever it is that's doing that, that's doing the scattering, that is the material particle here, that's got the rest energy of this thing right here. If it is the electron, like I said last time, it would be 0.511 MeVs for the rest energy. This theta is the scattering angle of the photon. And therefore, cosine of that angle is just a regular number. It would be 0 if the angle was straight upwards at 90 degrees. It would be equal to 1 if the photon was scattered at 0 degrees, but you would notice if it was equal to 1 that there's no shift, and that seems to make sense. This is the one in which the photon completely misses. And if it is backscattered, let's talk about that as an example. If the photon is completely it has a head-on collision, straight on, and is backscattered. Okay, let's do that one, and let's talk about what the Compton shift is for that. So, traffic light, homework, and we're rolling. Okay. So let's examine an X-ray. Now, one thing that is different, and I mentioned in the last class, that the photoelectric effect typically uses visible light. It will also use ultraviolet sometimes, but it's kind of around the visible spectrum. In this case, in order to preserve the photon, or to have a photon after the scattering, we need to use relatively high energy photons, such that if a portion of their energy gets taken away, they're still here, but it can accelerate an electron reasonably well. Incidentally, I will add on one more thing here. For us, this electron will be non-relativistic. So you can imagine it gets a bit more complicated if this is a relativistic photon. Gosh darn it. This is a relativistic electron, makes things a little more complicated. So we will consider non-relativistic electrons. All right, let's start off with an X-ray. our incoming X-ray wavelength, which we know, let's suppose we have an X-ray wavelength of 0.01 nanometers. Okay, that's a fairly typical X-ray wavelength in the sense that if you think of the visible wavelengths, right, you'd be thinking of 500, 600, 700 of the nanometers. These are 1/100th of a nanometer. So in the several hundred picometers, okay? Let's suppose that this X-ray wavelength is then backscattered. And what that means is the photon had come in, hit the electron, and then completely reversed path. In other words, theta is 180 degrees here. Alrighty, let's calculate delta lambda from that. So if we're scattered, I should say we scattered off electrons. I forgot to note that. It's backscattered off electron. So that we have something to put into the denominator here. If we calculate that, then what we'll find is that the shift is extremely small. I mentioned that last time. This is 1240 eV nanometers, and off electrons, which is pretty much the smallest thing that we can use, more or less, that will scatter. MC squared for an electron is, as I remember it, 0.511 MeVs per, not per anything, MeVs. Okay, which means that it's 0.511 times 10 to the 6th EVs. And that's going to give rise to a fairly small factor out front here that basically determines what the size of the wavelength shift is going to be. So you can imagine that perhaps there are many times in which something like this happens, but if you're looking at something which is shifting the wavelength in the 1,000th of a nanometer, okay, in the picometer range, that's not going to be normally detectable. I mean, in the sense that we can detect it if we look for it, but it's really small. So if we're just, oh, look, there's a photoelectric effect happening, well, and that one scattered off, we're not going to notice that there's going to be a shift in the wavelength, right? It's just too tiny. So you have to use wavelengths that are in which you could notice a difference like that. All right. At 180 degrees, this angle here, 1 minus the cosine of 180 degrees, you would know this is going to be a -1. So this is going to end up being 1 plus 1. In other words, this is going to give us the maximum possible shift that there is. Okay, making the 90-degree angle would kill the cosine off, and that would just give us regular 1, and so the wavelength shift would be given completely by just the front factor here. But if we want the maximum amount of shift, we're going to consider backscattered. Photons, and that hopefully should make sense, because that's the biggest punch that the photon can give to the electron, right? Is the one in which it hits it dead head on, and it's not glancing off or anything like that. It's head on hitting and then bouncing directly straight back. Okay, so when you calculate this number, let's see here, you'll find it's 0.00486 nanometers. Okay, so let's take a look and see here. What is the outgoing kinetic energy of the electron here? All right. What's the outgoing kinetic energy of the electron? Now that I know the two wavelengths, we should be able to figure, excuse me, we should be able to figure this out. Reason A, if you look at the bar chart for energy conservation here, anytime you make a bar chart for energy conservation, you can then write down the energy conservation equation mathematically. Because if I erased what this was, but this is the photon energy here, this is hc over lambda on the incoming side. And remember, we have rest energies for the electron on both sides, and they both drop away. So here on the hc over lambda prime side, okay, this here is the outgoing photon energy, and it's leftover kinetic energy. Anything that's not included. It's just kind of like thinking about the photoelectric effect, right? You can kind of think of the incoming photon energy, and then it gets divided up into two things. Okay, in the photoelectric effect, we had the leftover energy becoming kinetic energy in the electron, and that's essentially what's happening in this case. Rather than thinking about liberating the electron from the material, we're thinking about what is the energy left in the scattered photon here. That energy plus the kinetic energy of the electron then sums to become what the initial incident energy was. So this energy equation becomes fairly straightforward in the sense that you can just look at the bar chart and write it down. So I would know that hc over lambda should equal hc over lambda prime plus the kinetic energy of the electron. And if I wanted to then find the kinetic energy of the electron, it would be a straightforward issue to use the lambda and the lambda prime here that I found. Well, notice I have not actually found lambda prime. I did find delta lambda though. Here's a place to be a little aware of math and not jumping to something that looks like it would be useful and turns out is not useful. So here's something that I have found often will happen. I'm going to look for the kinetic energy of the electron. So we're solving for kinetic energy of the electron. What does that look like? Well, it's hc times, if I pull this over to the other side and factor out the hc, I'm going to get 1 over lambda minus 1 over lambda prime. And gosh, lambda minus lambda prime here, isn't that basically kind of what delta lambda is? It's like negative delta lambda. It's very tempting to write something to do with delta lambda here because you've got what looks like a lambda minus a lambda prime here. But remember, it's not a lambda minus a lambda prime. It's the reciprocals of those things. And so you have to use all the fraction stuff to go in if you're going to do that. Typically what I would do is I would say it's hc 1 over lambda minus 1 over lambda plus delta lambda, like that, and reminding myself that no, you can't skip to something involving a lambda prime minus lambda or something here. This is not related to delta lambda yet. Okay, I have to go here. All sorts of cute stuff you could do with this. You could factor out a 1 over lambda and then make it look nicer, things like that. I think what we'll do at this point is just go ahead and plug the numbers in because that's seemingly what needs to happen. So we'll go with 1240 here for the EV nanometers. I know what the initial wavelength is. It's the 100th of a nanometer. I'm going to subtract off that same number now plus, hopefully I didn't run off the board here, except, oh no I didn't, good. So it'll be the original wavelength plus my shift, which we just calculated over here, okay? Remember now that's going to be a larger number in the denominator, thus making the overall fraction less than the original one, which is good because we do not want the kinetic energy to come out negative. That would not work physically. That would tell you that something's gone wrong. Let's see here, when you do this calculation, I ended up getting 40.6 keV. 40.6 kilo electron volts. So 40,000 electron volts. I know I mentioned this, that we are not going to deal with relativistic kinetic energies of the electron. But why don't we just see? Why don't we take a look and see, well, I've got a kinetic energy of the electron now. Where does it, like, what kind of velocity are we talking about? What if we hit it with some SR just to see what would the V be? Right? So let's take a look at this. Just to give you an idea of what I'm talking about, because this is 40,000 electron volts. That's a lot of electron volts. It's more than, like, say, 8. 8 electron volts is less than 40,000. So we gotta have some idea of what does this kinetic energy mean. Can you just look at it and go, oh yeah, I know, this is relativistic, this is not relativistic, this is way not relativistic. Where does this number lie? Just to get a little bit of context in when we're talking about kinetic energies of electrons. So let's just ask, how relativistic is this? Okay, this is not a good question as it stands right now. How relativistic is this? Who knows? Until you say, as kinetic energy of an electron. And because I just don't really want to continually write electron, I'd usually just use E minus for the abbreviation for an electron. Okay, so let's take a look at this. If you remember from last time, and maybe you do, maybe you don't, it's not a big deal if you don't. It turns out that the kinetic energy in relativity, so this is the SR kinetic energy of a material particle, would be given by gamma minus 1 mc squared. In other words, here we know what the kinetic energy is. Here we know what the mc squared, that's the rest energy of the electron, is going to be, and our goal would then to be figure out what gamma is. So if we know what gamma is, then we can either look at gamma and say, oh yeah, that's really not close to anything that's going to be going fast. That's a gamma that's close to 1. So it's really slow. Or we can actually just go in and mechanically calculate what the speed's going to be. So let's take a look here. We want to solve for the gamma factor. And that means I'm going to swing the mc squared underneath and add 1 to it. So gamma is going to be 1 plus this kinetic energy of the electron divided by the electron's rest energy, which is 1 plus 40.6 keVs. And if I look at the electron's rest energy in keVs, it's 500,000. Right? This is 511 keV. So 40 divided by 511, that's a number that's maybe about 0.1, but it's going to be about 0.08. I guess if this was 51 keVs, then I'd have 0.1, but I'm not even quite at 0.1 yet. I'm not at 10%. So this is maybe about 0.08. So that means my gamma is equal to 1.08. Now, you can look at that and say, okay, well, that's pretty close to 1, and I know that if V is 0, gamma equals 1. Okay, but so where are we lying with this? Well, if I look at V, and I want to solve for V, and I use the gamma factor from this, then I'm going to end up getting something like this. And I don't remember here exactly what I got for that, so let's see if I can just figure it out real quick. 1.08 squared, oops, 1.08, and I'm going to take 1 divided by 1664, and I'm going to subtract 1, and we're going to square root that whole shebang. Oops. And it looks like I'm getting about, really? 0.38? PHYS is at 0.38. Wow, that's faster than I would have thought. Well, maybe I got something a little bit messed up. I know I've messed up some calculations before, but gee whiz. 0.08 for that, plus 1. All right. Well, all right. 1.165. Yep, that's that. So I'm going to negate that, add 1. And then square root it. Yeah, I guess so. Okay, 0.37 I got that time. So, oh, well, it's going faster than I thought it was going. Nevertheless, that's not fast enough to be relativistic. So in other words, the time stretch factor is really only about 8%. Well, I guess that is maybe. Well, maybe that is. Usually, if you're looking for a rule of thumb, you're looking for something that's definitely well less than. Usually, I guess maybe I would say maybe like 5.05 here would be fine. 5%. Oh well, but we're going to consider it not relativistic, so that's okay. That is what it is. Just to give you an idea of how fast that's going, almost 0.4 light speed, and yet the time stretch factor is really only 1.08. Wow, amazing. Okay, I guess I didn't notice that. Let's take a look at another example in which we have a little bit more of a scatter, right? So in the sense that what do we have if I have X-rays scattering at 60 degrees? Right? So now I'm going to use X-rays here, whose energy I know, of energy equal to 0.662 MeVs. And they are scattering at 60 degrees. My target is once again electrons, and I'm looking for, this is once again off electrons. I'm once again going to look for what's the scattered energy of the photons. What's the, in other words, maybe E prime, if you like to think of it that way, with the lambda prime. And what energy what kinetic energy is the electron going to be picking up? Or what kinetic energies are they going to be picking up? So in this case, let's take a look here. Now I've got a situation where I have E equal to E prime plus kinetic energy of the electron. So in other words, basically this exact same thing here. Okay? The issue here is I know that I'm kind of looking for this, which means I need to figure out what that thing is. And in order to do that, I need the wavelength. That means I have to unpack this energy in order to figure out the wavelength of the incoming X-rays, figure out the shift of those X-rays, and then pack it back up into an energy. Alrighty? So this thing here, which is hc divided by lambda prime, is hc divided by lambda plus delta lambda. And that delta lambda is given by, I erased it, it's not here anymore, but that's given by the Compton shift formula. So this thing here is, once again, 1240 eV nanometers. We're scattering off electrons, so we're doing 0.511 times 10 to the 6th, EVs. And we're going to multiply by 1 minus cosine of 60 degrees. Since the scattering angle of the photons is 60 degrees, in other words, they come in like this and pop up. They're going, they're not going at 90, they're going at 60, and the electron's getting kicked off this way. Okay, so when you calculate the delta lambda of this whole situation, I'm getting 0.00121 nanometers. And by the way, last time I got 0.00486. This is typical, right? In the thousandth of a nanometer. This is what you should be looking for if you're doing Compton shifts calculations. Something in the thousandth of a nanometer. If it's a lot more than that, maybe have a little red flag go off in your head telling you, wait a sec, did I do something? Yeah, you're not going to get a Compton shift of like 1 nanometer. Okay, so just, yeah, something to be aware of. Okay, so what I have to do now is take this and add this to the original wavelength. And the original wavelength, I would need to find that from using this as being hc over lambda equaling 0.662 times 10 to the 6th EVs, right? So if I flip-flop the wavelength with the energy in order to figure out what the wavelength is, 1240 on the top side here, because I'm still working HC. This is still going to be 1240 EV nanometers. And now I'm going to divide off the EVs. And I'm going to get an answer in nanometers. All right. Okay, so when I add these two together and I get lambda plus delta lambda, this is going to end up being 1240 EV nanometers divided by lambda plus delta lambda. So when I add those two together, I get, what did I get? I got 0031 nanometers. And that leads to an energy of the photon, which I got 402 keVs. All right. Okay, so finding the energy in the scattered photon. If I only have the energies of the incoming photons, right, like I described, take them all apart, find the wavelength shift, add that wavelength shift to the original wavelength, pack it all back up into an HC over lambda type of looking thing here, and then figure out what your new energy looks like. So here's my new energy. It's 402 keV, which means that the electron picked up quite a significant chunk of kinetic energy this time. Since we said 40 keV turns out to be about an 8% increase in the time stretch factor, this is going to result in a significantly larger effect in the time stretch factor because the original energy coming in was 662 keV. The outgoing photon has 402 of those, which must mean that the electron energy is 260 keV. Which is about half of what its rest energy is. So thinking about a quick calculation of the gamma factor in this case, you can see here that gamma would be 1 plus 260 keV over 511 keV, and this is about equal to 0.5. So gamma here is going to be 3 halves. And let's see, if I remember off the top of my head, that means it's something like, it's going like 0.6 or 0.8 or something like that, if I remember right. So it's chugging along pretty good in this case. Nonetheless, we don't have to worry about that, in the sense that, we don't have to worry about what it's going to do after that. Just finding the kinetic energy of the electron is reasonably good enough. If we wanted the velocity of it, we'd have to go in and use special relativity in the gamma factor like I did before. Now, if this was just a regular, more non-relativistic problem, what you might have ended up with something like maybe 200 EVs instead of keVs. And then you could use, suppose that we had something like the kinetic energy of the electron being 260 EVs. Okay, then you'd definitely see that that's not going to be an issue here. That's going to make the gamma factor equal to 1 plus about 1,000th. So the time stretch factor would be really tiny. In that case, if I wanted to calculate the speed of the electron, I'm going back to Newton for this now. Okay, this is definitely non-relativistic. And non-relativistic is NR. SR, GR, NR. Right? So I'm going to take this, and I'm just going to say, well, we already know what's going on here. This is 1/2 mv squared. And if that's equal to 260 EVs, like that, knowing the mass of the electron, I can figure out what the speed is. Now, note, we are going to have a units issue if you choose to use the standard kilogram value for the electron. I just love that the electron mass is given in kilograms. What an absolute joke. That's like trying to measure the mass of an apple using Earth as 1. I mean, this is ridiculous, okay? So what's often a nicer thing to do here, I'll show you a little trick for this, is to go back to, I erased it, but go back to using the rest energy, okay? Since this is the mass of the electron, it's just the same as the rest energy divided by c squared. But don't actually divide by c squared. Watch what I'm going to do. I'm going to take the rest energy of the electron, which is 511 times 10 to the 3 electron volts per c squared. And I'm going to leave the c squared in the units. Okay? Just like we did with volts and electron volts, now I'm doing c squareds in the units. Now, look what happens when I put that into here. I'm going to get the kinetic energy equal to 1/2 times this number, right? The 511 times 10 to the 3. Oops, EVs, forgot the EVs. Okay. Now, wait a minute, I'm cheating. Well, I'm just not writing the c squared yet, because I've got a v squared here. So if I just put the v squared with the c squared, all I have to do is then push everything else over to the other side and solve for v over c, and then I'll get the amount of, I'll get the relative speed in terms of c, right? And that makes it a little easier. Then I don't have to really worry about multiplying or dividing by c squared, which is a huge, ridiculously large number. Right? So then if this is equal to 260 EVs, then what I'm doing is I'm putting the 2 over and dividing by that thing, and then I'm square rooting the whole thing. And I'm getting a value for V divided by C. Like this. So let's go ahead and do something like that real quick. This is going to be 260 times 2 is 520 divided by 511,000. And now I want the square root of that number. Square root. And this is 0.032. Okay, it is unitless because it's a V over C ratio. But this is telling you that it's going 3% light speed. Rather than 30% light speed, which was what the 40 keVs was doing. Well, that's definitely not relativistic. Or at least it's not a situation where we really need to worry about relativity. Alright, so that is the mechanics of how to calculate the Compton shift. I do want you to remember the mentality of the Compton shift, however, which is, it's an experiment which shows that light is composed of photons. And they can be treated as particles which carry momentum and energy and suffer collisions just like any other particle. And it was really this experiment that started to hammer in, yeah, this is a real way of thinking. This is a real way of thinking about light. It is this stream of particles that we can't then necessarily distinguish between, but as a whole, that's kind of what they behave like. Okay. Alrighty. So with that out of the way, let's get to the next bit. Well, this is not working super well. let's get to the next thing, which is what happens with this momentum. Now, we've talked about we've talked about momentum of photons, because in the sense of the Compton effect here, we talked about the momentum carried by the photon as it went in to hit the electron. And we said, well, in a very ridiculous hand-wavy type of way, we came up with the idea that the momentum of a photon is h divided by lambda. Okay, and once again, you could ask the question, how are we describing the momentum of a particle using a wavelength? Because that's what works. And there's all sorts of shenanigans and hand-wavy arguments that you can probably put to it. But the end result is that we have, like I mentioned last time, we have these two big models of physics essentially colliding here. We have the particle model, in which we think of mass as being just a point, and this is something you used in 4A quite a bit when you talked initially about forces exerted on objects and kinematics of those objects. Before you got into things like center of mass and torque and angular momentum, basically everything was just a material point, okay? And you exerted the force on it and it accelerated, and you said, oh, if I have a rocket or something I'm throwing, I'm just going to assume it's a point, and I'm going to exert all the forces right at that point. I'm going to assume everything's exerted right there, and it's going to go to do this, right? So you can use Newton's laws to do a really good calculation of what's going to be the future behavior of something like that under those forces. But what does it mean then to talk about a wavelength in this context? Well, it means that we have to think about the wave characteristic of the field, as well as that wave then being divided up into lots of little particles. So it was a person by the name of Louis de Broglie who first de Broglie who first said, okay, things are getting kind of weird. Why don't we make them weirder? So he suggested that matter particles also have a wavelength. In other words, he suggested solving for it in the opposite way. So, if you think of what this is saying, this is momentum equaling h over lambda, and h is just Planck's constant. It's just a number. That's not going to change. So essentially what this is doing is it's relating the momentum of electromagnetic radiation to the wavelength of the electromagnetic radiation. De Broglie is saying, what if you think of the momentum of a particle as being related to the wavelength of the particle? In other words, since P is equal to h over lambda, what he's saying is, what if we said lambda was equal to h over P? Mathematically, this is something that fourth graders would do, right? Well, all I got to do is swap that and put that in. It's just right. Okay, great. But physically, think about what this means. This is telling you that things with momentum will have a wavelength associated with them somehow. So even if you are a material particle, in other words, even if you would say that your momentum classically is mv, you would then say, well, h divided by that mv is going to tell me what kind of wave characteristics this thing has. So at first he submitted this as his PhD thesis, and it was rejected. So, as you do in those days, he sent it to Einstein and said, hey, what do you think of this? And Einstein read it and said, let me talk to your dissertation group. So he talked to the dissertation advisor and said, I think this is okay. You should give the degree, and they did, because it's Einstein. You don't say no, really. Well, I guess you can, but it didn't really work out for you. Okay, so we've got this going. The idea of material particles exhibiting wave-like behavior. This is, once again, a jump into territory that seems to be ridiculous. Unfortunately, there is pretty good evidence to suggest that this actually describes what's going on. So let's take a look at some of this. First of all, let's take a look at what kind of wavelengths we're talking about with different speeds. All right. So let's start with this. Let's start with this. Let's start by assuming some different speeds and looking at what the de Broglie wavelength is for that. Well, let's start here of finding lambda. Okay, so I said, why don't we just start off with a 10-gram bullet traveling 500 meters per second? That's something that's got momentum, right? You shoot it, it's going fast. It's going faster than the speed of sound, right? It's 500. And it's only 10 grams. So let's calculate the momentum of this and then see what its wavelength characteristic looks like. Okay. So for this situation, P is mv because it's definitely classical, it's not relativistic, and it's going to be 0.01 kilograms multiplying 500 meters per second, which means it's got a momentum of 5 kilogram meters per second, which you might remember if you're thinking about the classical units here, that kilogram meters per second is the same thing as a joule second. So 5, say, sorry, not joule second, Newton second. My bad. Whew, caught that one in the nick of time. Newton second. If I now look at what is the wavelength of this thing, it's h over 5 Newton seconds. And h, now I have to go back to classical units for this. Classical, right? Newtonian size units. I need to start thinking if I have a bullet and it's traveling fast, I'm going to say, well, this is a fairly slow, relatively large object, right? What do I mean by large? It's only 10 grams. Yeah, but compared to an atom, it's huge, right? So I have to use h in regular units of joules. So this is 10 to the minus 34 joule seconds. And I'm going to divide that by 5 Newton seconds. And I put newtons in a place where I didn't want it. So let me erase that there. And we'll put it here, Newton seconds. Okay. Now, Planck's constant in our units is ridiculously small, as you would probably imagine. It is the fundamental amount of discreteness in the universe, right? 10 to the minus 34th joules. This is a ridiculously tiny number. And I'm dividing this by 5, which doesn't really affect anything here. So it's going to end up being about 1 point something. So say this is going to be around 1.2 times 10 to the minus 34. Just a quick look at the units here. I've got a joule per Newton. It's supposed to be in wavelength units, which is just distance, right? What's a joule per Newton? Well, if you remember, a joule is really a Newton meter, so it does work out. A joule here is a Newton times a meter. So the newtons are going to go out, and this is going to end up in meters. And that means that the bullet has a wavelength of 10 to the minus, more or less, 10 to the minus 34th meters. Sorry, 10 to the minus 34th meters. Well, you might say on the bright side, it's 10 to the minus 25th of a nanometer. But I don't know how much brighter that is. 10 to the minus 22 of a picometer. It's 22 orders of magnitude smaller than a picometer. Well, so that's small, right? That wavelength is pretty tiny. In other words, what that's telling us is the wave character of this bullet is extremely localized and doesn't really go outside of the size of the bullet. Okay, in fact, it's so tiny that it's nowhere near even, what's the size of a nucleus? 10 to the minus 15th of a meter. Okay, this is still, what, 15 orders of magnitude less than that, or 18. Okay, so you're talking about something that is physically not observable. And therefore, if this is really a thing, in other words, if this is really a thing, there's no way we're ever going to observe it for regular, non-relativistic things that are large. Okay. What we need to do is find smaller bullets and fire them faster, right? Such that when this, or I guess slower in some sense, but make this MV, right? Make the momentum a number. When you compare it to the size of h, gives you a wavelength that is actually like, oh, that's not terrible. So let's look at doing that. I picked, what did I pick? I picked an electron with a 1 electron volt kinetic energy. So let's go do that. Actually, when I said faster speed, I guess I meant slower speed. So let's now look at a 1 eV electron. In other words, the kinetic energy of the thing is 1 eV. That's a much smaller bullet. Now, if I do the same type of calculation in the same units, let's do that. Well, I don't really want to do that. Let's see here. If I want to do, yeah. So if we do this, let's do this. I'm going to say that the kinetic energy is equal to 1/2 mv squared. But really, we don't need either the kinetic energy or the V or the M. What we need is the momentum. And kinetic energy, you probably know, can be written in terms of momentum as p squared over 2m. So, since I want the momentum, a useful thing to do here is to write the momentum as the square root of 2 times m times the kinetic energy. That doesn't look very good. Can I just write K at the end? 2mK. And then, if I look at the lambda that's produced by this thing, h over this momentum, let's see, square root of 2mk. I guess I'm gonna lie. I lied. I said I was going to do it in regular units. I don't want to do it in regular units. It's an electron. No, all right, I'll do it in regular units. Let's do it this way. just to give you an idea. So this is why we don't do this. 6.63 times 10 to the minus 34, again for the Planck constant, that's in joule seconds. And I'm going to divide this out by the square root of 2 times the mass of the electron, which is 10 to the minus 31 kilograms. And the kinetic energy, but I need to convert the kinetic energy out of electron volts and into joules. Fortunately, the way to do that is just by using the charge of the electron. An electron volt is basically like a unit of energy, right? So we just have to use the electron charge to convert it into joules. That means it has an equivalent of 1.6 times 10 to the minus 19th of a joule's worth of kinetic energy. If you're interested in why that is, it's because, I don't know if we've gone over the conversion factor for that. I think we haven't. So an electron volt, right, is the same thing as an electron charge times a joule per coulomb. A voltage is basically an energy per charge. And so what you're really doing here is saying the amount of energy in 1 coulomb is such and such amount, but you don't have 1 coulomb, you have only an electron. So therefore what you'd say is it's electron 1 eV is therefore equal to 1.6 times 10 to the minus 19th, because that's the electron charge of coulomb times a joule per coulomb. And that is what gets you into joules. All right? So that's the conversion between EVs and joules, should you like to do that. Now, this is a horrendous calculation. I mean, look at this. There's 10 to the minus 34 and 10 to the minus 31 and 10 to the minus 19 and square root of this and it's a lot of big numbers that are a lot of little numbers that you don't really want to deal with. The point being here that when you everything is said and done here, you get a number that's about 1.2 nanometers. 1.2 nanometers, now that's useful. That's very useful. So if I have an electron with a wavelength characteristic of 1.2 nanometers, well, I can do things with that. And you might ask yourself, well, what can you do? Well, we just finished talking about things that act like waves when they go through double slits or single slit or apertures or diffraction gratings. Well, if I have that wavelength for this particle, then I can test to see if I do actually give a kinetic energy of 1 electron volt to an electron, and I put it through a diffraction grating, does it act like it has that wavelength? And the answer is, yeah, it kind of does. What if I put it through a double slit? Yeah, it does. So matter particles have this wave-like characteristic to them. And it's really only noticeable in the very, very tiny. So in order to compete with Planck's constant being this extremely little number, in order to compete with this, you have to have a really, really smallish momentum. And that comes about, in the classical sense, from having a really small mass. Okay? Really small mass. So the end result is something that's really tiny. It could be moving somewhat quick, but the fact is that it's so small that it's going to at least give something that is that's going to be an observable result here. Okay. The idea is that anything that has a wavelength can interact with something that's around the size of that wavelength. So think about for a minute the diffraction experiments and the double slit experiments that we did with the flea comb and with the cheesecloth. Now those spacings were huge, right? When you think about wavelengths of light, the light's wavelength is say 500 nanometers, and we're talking about something that's like a quarter of a millimeter, or maybe 1/10 of a millimeter. So that's still about 10 to the minus 5, right? So you're thinking about a spacing or a slit width of something that's around 10 to the minus, well, let's say 10 to the minus 4 of a meter, a tenth of a millimeter, okay? Whereas the wavelength of light, visible wavelength, is, say, 500 times 10 to the minus 9, which is about 0.5 times 10 to the minus 6. So let's say it's around 10 to the minus 6. That's a factor of 100. Okay, so a factor of 100 here would mean that something of 1 nanometer size could potentially be interacting with something that's 100 nanometers in size. And still you'd be able to see the wavelength effects that happen from things like diffraction. So just to give you an idea, this is an active area of research. The question people are asking is, when do we stop seeing this type of relationship? When do material particles stop having a wave-like nature to them that's detectable? Right? Now, in principle, the answer is never. But I will tell you that it is pretty unsettling, because what they've managed to do, I don't know if you know what a buckyball is, but it's a set of 60 carbon atoms, not just one electron, right? They've taken a full carbon atom, which is 6 electrons, and a nucleus that's really heavy, right? And they've taken 60 of those things, and they've seen wavelength effects. They've seen diffraction of C60s through an aperture. That is astounding. That's like driving a dump truck through a toll plaza and suddenly having the dump truck appear on the other lane over there. It's wacky. So I guess I would preface the rest of this with, welcome to the weird world. I mean, if you've been reading about quantum physics before, you've probably run into the idea that people say, oh, nobody understands this. And someone no less than Richard Feynman said exactly the same thing. I'm pretty sure that it's safe to say. No one understands this, and so I don't understand it. And so I'm happy to bring you into the world that you don't know, and pretty soon you won't understand it too. And you can then feel free to go spread this ignorance that we have to a lot of your friends, because we don't know. There is no physical intuition that we can grasp that will give us insight as to how this works. And I kind of mentioned this before, that the physical analogies kind of start fading away here, because this is a totally different world than what we're used to. Now, with that being said, what I'd like to do is, I don't know if skip is the right word, but I'm going to combine a couple of things that I wouldn't normally combine. And what I'm going to do is, I want to talk about the development of the model of the hydrogen atom. So maybe you've had a chemistry class or something which has spewed forth a bunch of lies about how this works. So I'd like to maybe help set the record straight, if possible, that the development of the model of the hydrogen atom was a really fascinating process. And we'll talk about a little bit of the physics behind it here. And I don't want to act like chemistry people and then just get to the whole thing about, oh, this happens, this happens, this happens. Let's talk a little bit about why we think it happens. This story kind of starts way back in 1884 with light, okay? And someone who noticed that what was interesting was, just at that point, high voltages became something that people could easily get. Okay, so it was the development of what's called the Van de Graaff generator. and things like that, where higher voltages became a thing that was not onerous to create. Now, when that happens, what people were able to do, what scientists were able to do, was take a sample of gas and just kind of run a spark through it and look at what happens when light is emitted by this gas. So the gas, in this case, hydrogen, certainly is a big component of the sun. And so if you look at the sun's spectrum, you'll see the big rainbow, right? There'll be a few differences in it, but those differences are interesting. It's like there'll be a little dark line right here, and then another dark line over here, and another dark line over there. And you say, why are these dark lines in the middle of the spectrum of this sun, which should be emitting everything? Why are there missing wavelengths? And so they started to think about, well, what happens when we look at the gas? If we look at the gas and the light that the gas can emit, it comes out in specific wavelengths. So the first thing that was noticed here was that the spectrum of hydrogen gave visibly only 4 wavelengths. And I can really only see 3 of them because one of the blue is really hard to see. The spectrum of hydrogen it gives only about 4 wavelengths. In other words, it looks something like that. Whereas you look at the sun and you'd see red, orange, yellow, green, blue, indigo, violet, right? You'd see all this great stuff. But in hydrogen, there's only these 4 lines. This is a red line. This is a turquoise, and kind of a green, blue, and then these are blue, and this is like a violet one here. But this is not at all a black body spectrum, right? A black body emits all wavelengths. Okay, yes, it has a peak, but it emits basically almost everything. This is emitting very distinct wavelengths, and it is not at all a rainbow. So this, when you say, how do you get the spectrum of hydrogen gas, this is from what's called a discharge tube, where it's a tube with hydrogen gas, and basically you put a shock through it. It's exactly like what we now use as a fluorescent light tube, with a relatively high voltage. Applied. Okay. And then when you look at the light that's coming out, what you would have to do is look at it through a diffraction grating in order to separate out the wavelengths. But you see only 4 wavelengths. And so the question is, why are we seeing only 4 wavelengths? How come we're not seeing everything? Why are we not seeing a full spectrum here? And it came down to a couple of people, Balmer and Rydberg, who developed basically a description of what the wavelengths are. And eventually it came down to Niels Bohr, who came up with a physical model that describes why these wavelengths are emitted from hydrogen gas. So I'm going to skip over a bunch of things, like the Balmer and Rydberg. I'm going to skip over the historical perspectives of that, but I'm just going to give you the end result, what they did, and what was eventually reproduced by Bohr when he made his model of the hydrogen atom, is that they said that these energies, right? You typically would say that it's the energies of these wavelengths, right? In other words, hc over lambdas. In terms of energies, energy.
like so. Change this, add on visible here. Okay.
Balmer was the first one to come up with a mathematical description of the pattern of the wavelengths, because the wavelengths were known. And he came up with a pattern for it, and it was Rydberg who kind of messed around with it and came up with a different way of thinking about it. But ultimately what they came out with was something like this, where if you wanted to figure out the energies of these photons, what you would do is you would take the number 13.6 and you would take 1 over 2 squared, and then you subtract off 1 over 3 squared, 4 squared, 5 squared, and 6 squared, and that would give you these numbers, right? So you would go 3, 4, 5, 6, like that. And that would reproduce the energies, which would then give you the wavelengths. Okay, so this thing here, you would say equal to hc divided by lambda, and those lambdas you could find.
So at this point, that hasn't shed any physics on why the spectrum looks like this. It's just a formula, right? This is like describing the position and velocity and acceleration of a particle as it moves along. It doesn't give you any physical insight as to why the particle is moving that way. For that, you would need Newton's laws. What are the forces involved, right? And that tells you what's the mass of the thing, that type of thing, all right? So when you look at what the model is that Bohr came up with for this, he was actually really excited about it, because what happened was he found out that I can reproduce these wavelengths if I consider an electron jumping between spots in an atom. And his model was initially a totally classical model. It comes out of the idea of planets around the sun. And it's not really based, we know better now, let me put it that way. But at that time, it was revolutionary in terms of thinking maybe we know something about what atoms are like, all right? So when this came out, there were a few things that we knew about atoms, okay? And one of them was that they have a nucleus, and it's really small. And they also have electrons somehow associated with them, okay? So the state of the atom in Bohr's time was that we knew, due to Rutherford's experiments,
Rutherford showed that there's a nucleus. All right, so there's a nucleus exists. Thomson showed that electrons exist. Because he took lots of different atoms and always found out that electrons are emitted if you heat them up. Okay, so from this, Bohr took these two things and said, okay, what if we put the nucleus here and have the electrons go around like this? So for example, there might be an electron in this orbit here, there might be one in this orbit here, might be another one over here, okay? So there they are. And they're spinning around doing things.
And when one of the electrons goes and jumps into a different orbit, Bohr said it emits a piece of light. And when he calculated what the orbits were, and then he calculated the energy differences between those orbits, those energy differences turned out to be exactly the energies of the photons that are emitted. But I see that we are just about out of time here for today. So we will pick up with a little bit more on the atom and wavelengths, how this all kind of fits together into a little bit more modern of a picture. We'll bring a little bit more of the semi-classical picture, working on that tomorrow, and then start transitioning into the more modern formulation of what to do and how to do it. Because ultimately I can tell you kind of how we think about it, but as we know, that doesn't really make big of a difference. Alrighty, so that'll be it for today, folks. I will post the homework and we'll get going. So good luck to you, and we'll see you soon.